First, I want to acknowledge and thank all my collaborators. This work really comes out of a lot of conversations with a lot of folks. Specifically, I want to acknowledge Leonardo, who has been my contact with helping me with this simulation software I've been using, which is called SynchroSim, and has a module called STSM, which is specifically set up for these types of questions, working with STM models. So just in case everyone isn't familiar, state and transition models are models to help land managers understand land potential and the mechanisms under which change in state might occur. So you have a state that a land parcel could be in, such as shrubland or a black gram or grassland, and then a mechanism such as overgrazing that could cause that land to change state.
Yeah, I just got back on. I got kicked off.
Oh, good. All right. So these models typically contain a lot of detail. I know we've heard a lot about them the last talk or two. I just want to remind you that they're often very detailed down to the species level, because I'm going to take this in a slightly different direction than a lot of folks have talked about these before. So these models are generally used for small parcels of land and for near future predictions. So what's going to happen in the next year or two to this land. But we run into problems if you're interested in a large area, or if you want to make predictions, say 50, 100 years into the future. And so we found that we need additional tools in order to address questions of scale. And one way we can do this is with simulations. The first step in this involves turning the mostly qualitative STMs into quantitative models. And we do that by assigning a probability to the transitions. So say you have some land that's in a particular state, the trigger occurs, what is the probability that that piece of land will transition to a new state? As you might imagine, it can be pretty difficult to estimate those probabilities with any kind of accuracy. And so the approach that I'm taking is to use remote sensing data to detect the rate at which past changes have occurred, and to use those rates as a basis for future predictions. Remote sensing has the advantage of being available for very large areas and going back in time. Specifically, 1986 is when our first really good Landsat remote sensing satellites went up. So I've been using the Rangeland Analysis Platform, or RAP, which estimates yearly vegetation cover broken down into classes. So you get shrub cover. I think these maps I've chosen are showing perennial grasses and forbs. You can get bare ground cover. And I'm applying this to my area of interest, which is in southern New Mexico. So in order to estimate those transition probabilities, if I can detect the states from this RAP data, I can then count the pixels that change states between 2 points in time and use that ratio as an estimate of the probability of changing between state 1 and state 2. But the first thing I had to do in order to detect states